Hello students, today we will discuss about another dynamic scheduling mechanism which is called as hardware based speculation. We have already discussed about one of the dynamic scheduling mechanism which is called as Tomasulo based approach or Tomasulo based processor, which uses the support of dynamically rearranging the order of instruction that is to be executed without affecting any of the hazards related to read after write, write after write, etc. So in the case of Tomasulo based processor, they are using additional hardware requirements like the usages of reservation stations, which holds the instructions and operands required for the immediate functional unit. It also uses a common database to deliver all the results produced by all the functional units, and that is to be communicated with the reservation stations as well as to the register files. So by renaming several registers with different names and also by getting the informations properly by delivering the result to the common database and by managing different situations dynamically by rearranging the order, we can have a solution for the insertion level parallelism that can be improved with the support of dynamic scheduling by using Tomasulo's approach. Now today's session we will discuss about another hardware based technique that is called as hardware based speculation, which is actually a variation of Tomasulo based processor. So we will see the variations that are actually added to the hardware based speculation. So it is normally applied to the case where we are having wide issue processes. When we use wide issue processes that may need to execute a branch every clock cycle. So some of the processor that uses several number of branches, and in every clock cycle they need to perform some branch operation. So we need to have some enhancement on such type of processor because branching normally costs more. So if in every clock cycle, if you are having more branches that are to be executed, we need to have some solution for this particular situation. So by exploiting more parallelism on this requires that we overcome the limitation of the control dependence or the branch hazards. Overcoming control dependencies is done by speculating on the outcome. So as we have mentioned in the branch prediction mechanism, we are actually following some of the possibilities that happens with branch prediction. So we are actually applying some speculation. We are taking some guesses on what may happen with the control or branch statements present in a particular set of instruction set. So we are doing some speculation that is based on hardware and which is applied on the outcome of branches and executing the program as if our guesses were correct. So we will proceed with the guesses are correct. Always we are predicting. We are doing some speculation on the branches and we are moving forward with the guesses are correct. This mechanism is an extension of our branch prediction with dynamic scheduling, which was already discussed in the previous session. Now with speculation, we do the fetch operation, issue, execute. These three operations are the major operations that are part of the 5-stage architecture. Now here in speculation also we are doing all these operations as if our branch predictions were always correct. So we'll go through all these stages by assuming that our predictions were always correct. It only fetches and issues such instructions that assumes that the prediction is always correct. Now the hardware-based speculation combines three key ideas. First is the dynamic branch prediction. We need to predict what will be the behavior of the upcoming branch. Then the second point is speculation, to allow the execution of instructions before the control dependencies are resolved. So we don't know what will happen with the real control operations or branching statement, what will happen. Before that, we are just making a speculation on how that will be working, that will be branched, or that will be predicted. Okay, so we are simply assuming that that branch will be behaving in this way and will continue with the steps related to that particular branch. So it may be wrong later, but we are assuming that it will be working as our guesses are correct. So it allows the execution of instructions before the control dependencies are resolved. That may be happening later, and with the ability to undo the effects of an incorrectly speculated sequence. So later, in some situation, if our speculation is wrong, it must be undone on that particular situation. And the dynamic scheduling is also being done to deal with the scheduling of different combinations of basic blocks. So these are the three key ideas related to the hardware-based speculation. It follows the prescribed flow of data values to choose when to execute the instructions. Then it executes as soon as the operands are available, as in the case of our Tomasulo based approach. An instruction is allowed to execute and to bypass its results to other instructions without allowing the instruction to perform any updates. So it allows the instruction to perform, it is not allowing the instruction to perform any updates until the final guesses are correct. Until we know that the instruction is no longer rough. So we are making a speculation, go through the execution of all the stages, and we do all these operations, but the final updations will be done only based on the final real assessment of the expected result of that particular branch that we are considered for speculation. Using a bypassed value is like performing a speculative read. We don't know whether the instruction providing the source register value is providing the correct result. We don't know whether how that branch will be performing, whether it is going this way or that way. We don't know the exact correct result. Some other stage only will be having the expected result of that particular case. But when an instruction is no longer speculative, we allow it to update the register file or memory. When an instruction is no longer speculative, when we cannot further do speculation, we will do updation on the register file or memory. So we will go like our speculations are correct, our guesses are correct, and we will continue, and we will update only after completing, or when we cannot have no longer speculation available. This additional step in the instruction execution sequence is called as instruction commit. So we are having one additional step called as instruction commit is present in the case of hardware based speculation. So that is a major point to be considered. So when compared to Tomasulo approach, we are doing the stages almost similar to the case, but here we are giving some guesses, and based on the guesses we are continuing and doing all the operations, and finally we are doing an instruction commit that is the last stage. In that situation only all the updates will be made during this speculation operation. So the key idea of hardware speculation is to allow instructions to execute out of order, similar to the Tomasulo approach, but to force them to commit in order. So we'll be having some order of order of instructions available. Then based on some speculation the order will be rearranged, but finally all the instructions will be executed in the same order, that is as it arrives into the system. It forced them to commit in order, so all the instructions to be committed in order, but in between it is executing out of order. But finally after the speculation all the instructions to be committed in order. So initially we are having one pipeline order available, so there will be some problems, like there will be some hazards available, some data dependencies available or output dependencies available. So there will be some dynamic variation of the order based on some branch expectations, guesses we are moving towards. But during that we are not updating any value. But finally after before completing that procedure we will do a final commit, that is called as insertion commit. In that situation all the insertions will be committed in order. So insertions arrives at one order, executes in different order, finally commits at the initial order. That is happening with the hardware based speculation mechanism. Now adding the commit phase requires an additional set of hardware, that is always an additional cost. This holds the results of instructions that have finished execution but have not committed. So the additional hardware holds the results of all the instructions that have finished but not being committed. So using that hardware we will be having the reordering of the instructions that is to be committed. So this hardware buffer is usually called as reorder buffer or ROB. Is also used to pass results among instructions that may be speculated. So it holds all the results among different instructions and that is to be committed in the order as it is arrived at the initial stage. The reorder buffer provides additional registers in the same way as the reservation stations in Tomasulo algorithm extend register set. It also holds the result of an instruction between the time the operation associated with the instruction completes and the time the instruction commits. So it will have all the time informations also along with the reorder buffer. So we are having one additional hardware component called as reorder buffer available with the hardware based speculation mechanism. Using that we are maintaining some more informations, means all the intermediate results, and finally that buffer will be committed in the initial order itself. Now this ROB is a source of operands for instructions, just as the reservation stations provide operands in Tomasulo's algorithm. So ROB consists of all the operands before the final commit operations, similar to the reservation stations available in the Tomasulo algorithm. Now what are the differences between the ROB and the reservation station? That is, first one is in Tomasulo algorithm, once an instruction writes its result, any subsequently issued instructions will find the result in the register file. So it will get the results from the register file in the case of Tomasulo approach. But with speculation the register file is not updated until the instruction commits. So normally Tomasulo approach, every instruction can refer to the register file for getting the current updated data. But in the case of speculation, the register file is not updated until the final commit happens. So that is a major difference between the register file and the usage of ROB in the case of hardware-based speculation. The reorder buffer consists of 4 fields: the insertion type, the destination, the value, and ready. So the insertion type field indicates whether the insertion is a branch or a store or a register operation, what type of insertion it holds. Now second one is the destination field. It supplies the register number or the memory address where it is to be stored, or where it is to be written. Then comes the value field, which is used to hold the value of the insertion result until the insertion commits. So before getting the final committed results, it will store the intermediate insertion result into the value field. And finally we are having a ready field, which indicates that the insertion has completed execution and the value is ready. It is like a status indicator of whether the value after the execution is ready or not. So we are having 4 fields of reorder buffer: the insertion type, the destination, the value, and the ready field. Now this is the architecture which is of the hardware based speculation. Now from the insertion unit we are having all the insertions which is in first out order, and the insertions are given, all the load store insertions are given to the address unit, and address unit, from the address unit the load, through the load buffer, it is connected to the memory unit. Now you can see that here we are not having any store buffers available. The store buffers are not available here, but the store buffers are actually directly connected to the reorder buffer. All the store informations are with the reorder, because the store is not done directly to the memory unit. The store is done only after getting the result. It will go through the reorder buffer, and after doing from the reorder buffer it is to be committed, and that final value only need to be stored into the memory unit. That is why we are not maintaining any store buffer here. That was there in the Tomasulo diagram. Okay, so this is the load store operation. Then when it comes to floating point operations, as usual it will go through the reservation station. So reservation stations are used for, just like the previous case, that is for register renaming, for storing the instructions and operands which are expected by these functional units, and if it is not available there, it will take the data from the floating point register through the support of reservation stations. Then the units will produce result, and result is given to the common database, through which it will go again back to the reservation stations, and it will also go to the reorder buffer, through which it comes to the floating point register, because after the temporary results will be stored in the reorder buffer. Then later at the final stage it will be committed, then only the result is stored into the register or into the memory address. So each time after all these stages the intermediate results are given to the reorder buffer. Also all these are temporary results, that is not the final updated one, but before finalizing or after completing all the stages, it will go for a final insertion commit, and after that if the result is to be stored into the register, it will communicate with the register. If the result is to be stored into the memory address, it will be communicated with the memory address. So this is the major difference between Tomasulo's approach and hardware based speculation. So this is an enhanced version of Tomasulo based processor. So we are using the same reservation stations here, we are using the same common database here, we are using the same FP registers here, we are using the same instruction queue here, address unit, memory unit, FP address, FP multipliers, load buffers, but store buffer we are it is connected to the reorder buffer. So the additional hardware for our hardware based speculation is the reorder buffer, where we store the result that are produced by various components, but reorder buffer is to be updated finally for getting, after the speculation, after that area is completed, we will get the real result by doing final insertion commit, and then the result is stored into the different components. So the reorder buffer absorbs the store buffers. It holds the store buffer also, as I was indicating by explaining the diagram. The store still execute in 2 steps, but the second step is performed by the insertion commit. So final store will happen only after doing the final commit. Renaming function is replaced by the reorder buffer. Now the renaming is done with the support of the reorder buffer. Before, in the previous case, it was with the reservation stations. Now it is happening with the reorder buffer. Since every instruction has a position in the reorder buffer until it commits, we tag a result using the ROB entry number rather than using the reservation station number. So here every time the instructions are identified by using the ROB entry rather than using the reservation station number. There are 4 steps involved in the insertion execution, as in the case of Tomasulo based processor. The first stage is the issue stage. So that is the after insertion fetch, insertion decode is divided. So first we are having issue stage. It will get an insertion from the insertion queue, issue the insertion if there is an empty reservation station and an empty slot in the ROB. Issue the insertion if there is, so it will look at both reservation station as well as ROB. If there is an empty slot, it will issue the insertion. So both reservation station and ROB must be empty for entering the insertion. Previous case, it was only looking for the empty space in the reservation station. Now send the operands to the reservation station if they are available in either the register or the ROB. So through register or ROB, there is the operands to be moved towards the reservation station. Then update the control entries to indicate the buffers are in use. We need to update the control entries, means branch related entries, to indicate the buffers are in use. If either all reservations are full or the ROB is full, the insertion issue is stalled until both have available entries. That means if ROB or the reservation stations are full, it is the indication of having a structural hazard. Then the next stage is the execute stage. In the execute stage, if one or more of the operands is not yet available, just look at the CDB common database while waiting for the register to be computed. It will check for row hazard. When both the operands are available at the reservation station, then go for execution. Then it may take a more number of cycles, depends on the instructions. Third stage is write results. When the result is available, it will write the result to common database, then to the reorder buffer as well as to any reservation station. So result will go to ROB and reservation station that is waiting for the result. Then mark the reservation station as available. If the values to be stored is available, it is written into the value of the field of the ROB, value field of the ROB entry for the store. And if the value to be stored is not yet available, the CDB must be monitored again and again whether the value is currently available. So if the value is available, move the value to the ROB. We need to have an entry on the reorder buffer. And finally, we are having the last major crucial stage, that is called as commit. So in the Tomasulo approach, we are having only issue, execute and write result, but here we are having one more stage which is called as commit. Now in the commit stage, we need to complete the instruction after getting the results. So there are three different sequences for a branch with incorrect prediction, a store, or any other instruction. That is for normal commit. There are different situations for branch, whether it is to be committed or not. Now in the normal commit, the processor updates the register with the result and removes the instruction from the ROB. Now after completing the instruction, write, update and commit and write the results to the register and remove the content from the reorder, because some other entry need to enter into the ROB later. We need to make it free. In committing a store, the memory is updated. Similarly, the memory will also be updated while doing the final commit operation rather than a result register. So for store operation, it is always updating the memory. When a branch with incorrect prediction reaches the head of the ROB, it indicates that speculation was wrong. So if the prediction was incorrect later, finally, we are assuming that the branch will work in this way. Accordingly, we are moving towards, and we are storing the values in intermediate results into the ROB. But later it is identified that the prediction was wrong. That means the branch was wrong. What will happen? It is assuming that the speculation was wrong, or assumption or guess was wrong. Now the ROB is flushed. All the contents from the ROB will be flushed, and we need to restart the entire execution once again by executing the branch instruction once again. In practice, processes that speculate try to recover as early as possible after a branch is mispredicted. Now if the prediction was wrong, there is some recovery procedure, like we need to flush all the contents of ROB, and it is always trying to recover as early as possible to get back to the previous normal stage. Now this recovery can be done by clearing the ROB that I have already mentioned for all entries that appear after the mispredicted branch, allowing those that are before the branch in the ROB to continue, and restarting the branch at the correct branch successor. So we need to start from the previous branch once again. In speculative processes, performance is more sensitive to the branch prediction, since the impact of a misprediction will be higher. So normally the speculative hardware-based speculation is applied to the situation when we use branch prediction. When we are having more branches available with every clock cycle, if you are having some branch operations available, we need to follow these hardware-based speculation so that we can reduce the number of the wrong occurrences or issues related to the branch can be or the issues can be resolved by using the hardware based speculation method. So this is another one of the major dynamic scheduling mechanism. Now by using this mechanism, the write after write and write after read hazards are eliminated with speculation, because the actual updation is run it is done in the order of the arrival of instruction. So all these hazards can be because they are arriving at one order, executing in different order, but finally committed in the same order as it arrives. So there won't be any such type of hazards that may be created within this hardware based speculation system. Raw hazards through memory are maintained by two restrictions: not allowing to load to initiate the second step of its execution if any active ROB entry occupied by a store has a destination field that matches a value of the A field of the load. So we need to have some compromise when we use store operation and load operation. We need to have some order that is to be maintained. That means maintaining the program order for the computation of an effective address of a load with respect to all earlier stores. We need to maintain some program order properly for the case of load and store operations. So this is a second mechanism that is used for dynamic scheduling, a variation of Tomasulo based processor by adding an additional hardware components called as reorder buffer, which is used to store all the results produced in between the execution of all the instructions based on speculation. And finally, if everything is okay, the final result will be committed finally, and the results will be stored into the registers and other devices. And if the speculation is wrong, the entire ROB content will be flushed and we will restart from the branch instruction once again, so that we can avoid that wrong speculation. And next time we need to go for some more speculation, and based on that we need to identify whether the results generated are correct or not. Now we are having a last topic called as multiple issue and static scheduling. Multiple issue and static scheduling. Now to improve the CPE, to improve performance, CPE cycles per instruction can be decreased to less than 1. So sometimes normally the ideal cycles per instruction is 1 cycle per instruction, but for improving the performance we need to even reduce that into less than 1. It is possible only when we are having multiple number of issues available. The CPU cannot be reduced below 1 if you only issue 1 instruction at a time in a cycle. Now if it is possible to issue more than 1 instructions within a clock cycle, we can reduce the cycles per instruction to less than 1. So that is the aim of adding multiple issue and using static scheduling on that particular situation. So the goal of the multiple issue processor is to allow multiple instructions to issue in a single clock cycle. So normal ideal case, so far we are discussing about issuing only 1 instruction in 1 clock cycle. So every time we are considering it as 1 only. But in that clock cycle, if we can provide 2 instructions, the cycles per instruction can be reduced to half. That means 0.5 for 1 instruction and 0.5 for second instruction. Now multiple issue processors come in 3 major categories. One is statically scheduled superscalar processors. Second is very long instruction word processors. And third one is dynamically scheduled superscalar processors. So first and third one are superscalar processors. One is statically scheduled and second one is dynamically scheduled. And the middle one is very long instruction word processors. The 2 types of superscalar processors, the first and third one, issue varying numbers of instructions per clock and use in order. They uses in order execution if they are statically scheduled, and they uses out of order execution when they are using dynamically scheduled mechanism. So they are using both static scheduled and dynamically scheduled instruction execution. Now VLIW process issue a fixed number of instructions formatted either as one large instruction. So that is the difference between the previous superscalar processors. Multiple number of instructions are given separately in order or out of order. But in the case of VLIW processor, the fixed number of instructions, a number of instructions are formatted into a single large instruction. One single instruction, but it internally performs a number of other instructions. So it will be having a fixed instruction packet with parallelism among instructions present in that particular instruction packet. Now these processors are inherently statically scheduled and it is done by the compiler itself. Now statically scheduled superscalars issue a varying rather than a fixed number of instructions per clock. They are actually closer in concept with VLIW, since both these approaches rely on the compiler to schedule code for the processor. So superscalar as well as VLIW, only difference is the number of instructions are separate in the case of superscalars, but in the case of VLIW the same thing, it is given as a single packet, but both of them are actually done similar to the static scheduling with the support of compiler. Now VLIW, so we'll see some more details regarding VLIW approach. It uses multiple independent functional units. More independent functional units are available, so it will be highly performing. It packages the multiple operations into one very long instruction. I have already mentioned, or requires that the instruction in the issue packet satisfy the same constraints. The advantage of VLIW increases as the maximum issue rate grows. Now, because of that, we are considering a wider issue processor. Means more instructions are to be processed at the same cycle. We are mostly using VLIW approach. Many designers argue that a 4-issue processor has manageable overhead. A 4 instructions at the same clock cycle is a manageable one, but the growth in overhead is a major factor limiting wider issue. If you are multiple issues to be processed within the clock cycle, the requirement overhead cost will also be increased. So that is a problem related to the wider issue processors. To keep the functional units busy, there must be enough parallelism that is available with the VLIW approach. Even if it is present in a single packet, we are having multiple functions to be executed inside the VLIW package. The parallelism can be done by using loop unrolling and scheduling, as we have already mentioned in the previous sessions. Local scheduling can also be used for the unrolled loops. To find and exploit the parallelism require scheduling code across branches. It requires a global scheduling algorithm. It also requires a trace scheduling, that is one of the global scheduling technique developed specifically for this particular VLIW approach. In the earlier VLIW, there was no hazard detection hardware at all, but later we have got some hazard detection hardware is also being added into the basic VLIW approach. Now, this structure detected that a stall in any functional unit pipeline must cause the entire processor to stall. So one functional unit is under stall means it will affect the entire processor. Similarly, predicting which data access will encounter a cache stall and scheduling them are very difficult in the case of VLIW approach. Synchronization restriction becomes unacceptable in the case of VLIW approach, and the compiler is used to avoid hazards at the issue time in the case of VLIW approach. In a strict VLIW approach, the code sequence makes use of both the instruction set definition and the detailed pipeline structure, including the functional units and their different latencies. They are considering all these dimensions for a strict VLIW approach. Now, the different number of functional units and unit latencies require different versions of the code. That is also added to the VLIW approach, and this requirements makes migrating between successive implementations or implementations with different issues with. Now, the major challenges for multiple issue processors are to try to exploit large amounts of instruction level parallelism. that is seems to be a very difficult task. So sometimes we need to go for the usage of vector processor when the parallelism comes from unrolling symbol loops in FE programs. The loop could have been run efficiently on a vector processor. Now it is also not clear that a multiple issue processor is preferred over a vector processor for such applications. The cost will be similar and the vector processor is typically the same speed or faster. Even if it is a multiple issue processor or a vector processor, it is just like a normal processor. The potential advantages of multiple issue processor versus a vector processor are their ability to extract some parallelism from less structured code. We can have more parallelism on less structured code. Also the ability to easily cache all the data. We can have a temporary storage of data in the cache memory in the case of VLIW approach. And because of all these reasons, multiple issue approaches have become the primary method for taking advantage of insertion level parallelism. So this was an additional topic added to the scheduling. This chapter deals with the insertion level parallelism basics, then compilation techniques, then dynamic hardware based techniques, then finally we have selected a topic related to handling multi-cycle operations by reducing the number of cycles required for a particular task and the various approaches used for executing such instructions, that is like the system called as VLIW approach in detail was also discussed, and I hope that these topics will be useful for your real research oriented processor related studies and all, and I hope that this will be very helpful for your academic side also. So that's it for now. We will come with another session in the next video. Thank you.